All right, so in today's lesson, we are going to continue our notes and our discussion of the periodic table. Um, so today we're going to be talking about trends, things that we notice in the periodic table as we move from one side to the other. So as you move from the left side of the periodic table across to the right side, how do things and properties of the elements change? That's what we're going to be talking about today. So when we say a trend, that's what we're talking about. A general trend. A trend is generally how something changes from one side to the other. Does it get bigger? Does it get smaller? Does it increase or decrease? Now, one thing you need to make sure you understand is that when I say a general trend, it means it doesn't always do the same thing. There might be some instances where it gets bigger here, but then it gets smaller and then bigger and bigger and bigger and bigger and bigger and then smaller and then bigger. But overall, it tends to go up. Think about it kind of like if you've ever seen a stock market graph where it sits here and goes like this throughout the day, but overall throughout the day it goes up. It's a general trend. That's what we're going to be talking about. Now, there are four trends that we're going to be talking about, four properties of elements that we're going to talk about on the periodic table. Those are the only four that we care about. There's a lot more, but they're the only four that we're going to care about for this class. All right, so the first of those is atomic radius, which is the size of the atom. Now, we can't measure the exact size of the electron cloud because electron cloud is not really a solid thing. We can't actually measure that. We're going to talk more about the electron cloud in the next section of units, or the next unit. So we can't really measure the electron cloud, so we define the atomic radius. All right, remember, a radius of a circle, atoms are mostly spherical, and the radius is from the center to the outer edge. We can't really measure that outer edge, so the radius for metals is defined as the distance between the nuclei of adjacent atoms in a crystal. So solids, metals, when they are in solid form, you're going to have an atom here, an atom here, an atom here, an atom here. They're all touching each other. All right. So when we say adjacent, that means atoms that are touching each other, the distance between their nuclei. That is what we call the atomic radius. It's half of that distance. The total distance would be its diameter. So half the distance is the radius. All right. For a nonmetal, it's half the distance between atoms of the same element when they're bonded together. So like when hydrogen bonds to hydrogen, half that distance. When oxygen bonds to oxygen, half that distance. It has to be the same element. Otherwise, it doesn't really work because, well, the bond length is different when you have different elements combined. So that's the atomic radius. We'll talk about that bonding stuff later. Okay, so here you have a picture of the metallic radius, and you can see the distance is half the distance between adjacent atoms. And then for a non-metal, we have our bonded atoms together, and it's half the distance between them, measured in picometers, which are really, 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 really small. All right, so this is the atomic radius. That's the definition. That's what it is. Basically, it's the size of the atom. All right. So when you're looking at the atomic radius generally decreases from left to right across the periodic table. When you start out over here on the left side of the periodic table, as you move right, the atoms generally get smaller. All right. And if you look at this picture, you'll notice that you've got small atom or larger atoms over here, and they get smaller and smaller and smaller as you move towards the right. Now, this picture is only showing you the representative elements. It's leaving out these transition metals here in the middle and only showing you the representative, but the trend continues in the transition ones as well. And you'll also notice that from top to bottom, it generally gets bigger as you go up and down. So this is the trend for the atomic radius, is as you move from left to right across the periodic table, the atomic radius, the atoms tend to get smaller as you move from left to right. And as you move from top to bottom, they tend to get larger. They increase as you go down the periodic table, and they decrease as you go left to right across the periodic table. So that's atomic radius. All right. Excuse me. This decrease from left to right, so you would think that they would get bigger because you're adding protons, so you're making the nucleus bigger. But as you're moving from left to right, as you're moving across the periodic table, you are actually losing attraction, or sorry, you're losing repulsion. As you add protons, you're getting more and more positive charge in the nucleus, and positive charges are going to attract the electrons. So the more positive charges you have, the harder that pull is, and the more it pulls in, and the stronger that pull is, and so you get an increase in attractive force as you move. The increase from top to bottom is due to the distance that you have from the nucleus, because as we talked previously, you have energy levels, and each row represents a different energy level on that electron cloud. So as we add an electron, or as we add an energy level, you're adding a layer to that cloud. Think of it like if I'm going to put on a bunch of clothes. If I put on a jacket, then I'm a little bit thicker. That outer edge is farther away from me. If I put on another jacket, it's even farther away. And every jacket I put on makes it bigger and bigger and bigger. So even though the attractive force is getting greater by adding protons, you're also increasing the distance because you're adding a layer. So as you move down the periodic table, you're adding a layer every row that you add. And so the atom gets bigger and bigger and bigger as you move down the column. As you move across the row, the protons pull on those electrons more, and they pull them in. All right, that's the nuclear attraction pulls them in a little bit more. Now, ionic radius is very similar to atomic radius because it's measured kind of the same way. So when atoms lose electrons, they're going to form positive ions. Because they lose an electron, they've lost a negative charge. That means they have an extra positive charge. So they're now positive ions, all right? And they become smaller. And they become smaller for two reasons. One, they're going to lose the electrons on the outside, those valence electrons that we talked about before. They're going to lose the valence electrons on the outside. So if they lose those, then all of a sudden the electrons that are on the outer edge, the ones that define the radius, the ones on the outer edge, are actually closer to the nucleus now. Plus, you're losing an electron, so there's less electrons there to repel each other. So the electrons are pushing each other away. So at the same time that the protons are pulling all the electrons in, the electrons are pushing each other away. So there's this little balance between getting pulled in by the nucleus and pushed away by the other electrons. So if you lose an electron, there's less electrons pushing out, and so they get pulled in even more. And there's one less layer to that electron cloud, so it is smaller. So when you lose an electron and become a positive ion, a cation is going to be smaller than the atom was before. So for example, if I have lithium is this big, a lithium ion is going to be smaller. This example is sodium. So we have a big sodium. Well, sodium loses one electron in its outer energy level. Remember, sodium's over here in group 1, so it has one valence electron. It's going to lose that one valence electron, and suddenly it loses an entire energy level, so it shrinks. And then those protons pull on it even more, and so it shrinks even more. So it's significantly smaller. You'll notice 186 picometers versus 102 picometers. There's a significant difference there. All right. Now, when atoms gain electrons and form negatively charged ions, so they're gaining one, so they're getting more negative charges than they have positive. So they gain electrons. They're going to increase in electrostatic repulsion. So those electrons, now that there's more electrons, they're pushing out even more. So they're going to push out away from each other even more than they were before. And there's the same number of protons, and that new electron is added to the outer energy level that's already there. So they're not gaining an energy level, they're not losing an energy level, they're just increasing the amount of electron repulsion, the electrons pushing themselves apart. All right. And so when you add an electron, it gets bigger. So a negative ion is going to be bigger than the one before. So this is chlorine. Chlorine normally has a 100 picometer radius. Well, when it becomes an ion, it gains an electron. And when it becomes an ion, it's going to increase its radius to 181 picometers. So it gets bigger because now there's more repulsion of those electrons. Okay. The trend is important, but it's also important that you understand why. That's why I'm explaining it multiple times to make sure you understand. You have to understand why the trend is what it is. Why does the radius get smaller when it becomes positive? It gets, when an atom goes from a positive or from neutral to positive, it's going to get smaller because it's losing a layer of its electron cloud, and it's increasing, or decreasing, I should say, decreasing the electron repulsion. When an atom goes from neutral to negative, it's going to get bigger. It's going to increase its radius because you're increasing that electron repulsion. Those are your reasons. So ionic radius is generally going to decrease from this side of the periodic table across, from left to right across the periodic table, and it's generally going to increase from top to bottom. All right, because as you go down, same as the atomic radius, you're adding a layer. Even though you've got an ion, the ion stuff happening, you're still adding a layer to the electron cloud as you move down the row. So you'll notice that the trend for atomic radius and the trend for ionic radius is actually the same. It decreases as you go left to right, and it increases as you go top to bottom. All right. You will notice, though, that when you go from column 14 to column 15 over here, you will notice that the radius jumps up in size. It's because columns 1 through 14 all have positive ions. They all form positive ions. Once you get past row 14, they start making negative ions. And so there's this big jump. But from 15 over, they still get smaller. So when we say a general trend, yes, it does get bigger from 14 to 15, but it still generally goes smaller as you go left to right. And you'll notice on this little graphic here that there is not a column 18. And the reason there's not a column 18 is because, as we talked about before, the noble gases don't react with other things. They don't form ions. And so they don't have an ionic radius because they don't really form ions. So again, here's the periodic table with your general trends. They decrease as you go left to right, and they increase as you go top to bottom. This is your trend for ionic radius. All right. The third property that we're going to talk about is ionization energy. And ionization energy is defined as the amount of energy required to remove an electron from an atom when it's in its gaseous state. All right. So when you have an electron, an atom in its gaseous state, and you want to pull an electron off of it, how hard is that? If it's really hard, so a high ionization energy means that the atom really likes its electrons and it doesn't want to let go of them. A low ionization energy means it doesn't really care and says, take them away. All right. It doesn't take a whole lot of energy to remove electrons if it has a low ionization energy. So if you think about the same thing that we talked about before, the positive and negative attraction, as we are attracting things in, the positive nucleus is pulling those electrons in. Well, how hard that pulls determines how hard it is to pull them off. Think about this tug of war. If I want to pull the negative electron off, I have to pull harder than the positive nucleus is pulling. So my energy pulling out has to be greater than the energy of the nucleus pulling it in. Okay, that's what that ionization energy is, the amount of energy you have to use to remove that electron. Okay, so if I have a small atom that has a very close-knit, pulled-in atom, it's going to be a lot harder to pull the electrons off. The closer those electrons are to the nucleus, the harder it is to pull them off. The farther they are from the nucleus, the easier it is to pull them off. So that should tell you that the trend is going to be slightly, or going to be more or less the opposite of the two trends that we just talked about, radius trends, ionic radius and atomic radius, right? So this graph here shows you the energy required. You'll notice hydrogen has a relatively low ionization energy, whereas helium is much, much greater, all right? Because helium is a smaller atom, it's harder to pull them off. And you'll look at that as you go each of those rows. It shows lithium to neon, and each of those other dots there would be the ones across the row on that. The ionization energy basically gets bigger as you go across. Remember, as you go from left to right across the periodic table, the atoms themselves are getting smaller and smaller and smaller. Well, the smaller they are, the harder it is to pull those electrons off of the outer edge because they're closer to the nucleus. So as it gets smaller, it becomes harder and therefore a higher energy. So as you move from this side of the periodic table across, it gets higher energy. It becomes more energy required to pull that electron off. Okay? I don't know what those lines are there for. Ionization energy generally increases as you move from left to right because the closer the electrons are to the nucleus, the harder it is to remove them. More energy it'll take. And as you move from top to bottom, the ionization is going to decrease because the same reason the atom gets bigger, the electrons are farther away. The farther away they are from the nucleus, the easier it is to pull them away. So the lower you go down on the periodic table, the easier it is to remove an electron. And so those electrons get pulled off much easier, a lower ionization energy. And so this is our general trend here. As you move left to right across the periodic table, it generally increases. And as you move from top to bottom, it generally decreases. Now, electronegativity is a really weird sounding word. All right. Electronegativity is basically a measure of the relative ability of an element to attract electrons. So it's how much they want electrons, their ability to attract electrons. They pull them in. All right. So atoms or elements that give up their electrons easily are going to have a very low electronegativity. Atoms that do not let go of their electrons, they're not only do they not let go of their electrons, they also grab electrons and pull them in. So they're going to have a higher electronegativity. So atoms that are larger and it's easy to remove electrons, like these guys down here, are going to, they're the large ones that have a low ionization energy. Low ionization energy means it doesn't hold on to the electrons very well, and so it doesn't attract electrons very well. And so it's going to have a low electronegativity. Whereas ones over here are going to have a high electronegativity because they're going to pull on those electrons even more. Not only do they not let go of the ones they have, they want to take them from other things. Right? In fact, fluorine is the highest electronegative element. All right? And actually, fluorine's over here. As electronegativity increases from left to right until the noble gases and decreases from top to bottom. So again, the noble gases, they don't want electrons. They're not going to pull them in. They don't want to let go of them. They don't pull them. They don't want to take them from other elements. So we kind of leave them off the electronegativity one. But as you move from left to right across the periodic table, when you get over here to the halogens, you're going to have elements that love to pull electrons away from other things. So like I said a second ago, fluorine is the highest electronegative element. And francium over here is the least electronegative element. I had those flipped backwards a little while ago. Sorry. All right. So that is the end of our discussion of our trends that we have for today. So the 4 trends you need to remember, again, are atomic radius, ionic radius. Both of those are going to decrease from left to right and increase from top to bottom. And then you have ionization energy and electronegativity. And those are going to do the exact opposite. They're going to increase from left to right, and they're going to decrease from top to bottom. So if you just remember the atomic radius trend, this is what you need to remember. Remember the atomic radius trend, what it is, and then just know that the ionic radius is the same, and then electronegativity and ionization energy are the opposite. So the 2 radii have the same trend, and the 2 that have the E, electronegativity and ionization energy, are the same, and they're opposite of the other two. So you have two that are the same, two that are the same, and they're opposites of each other. So really, you only have to memorize one of them and then know how they relate to everybody else. But the other thing you need to make sure you know is why. So go back if you missed it. If you're not sure, make sure you understand why those trends are what they are. That's what you're going to be asked about. That's what you're going to be tested over, what the trend is and why. So thank you for watching and have a good day.